Hello students, last day I have started the issue related to digital communication. In this regards, I want to tell you something about digital modulation technique. There are two digital modulation techniques. One is the known thing, very common issue related to base band modulation, where the baseband signal is converted in terms of digital form from the analog nature. This kind of the conversion is known as baseband modulation. Information that is absolutely same, but the nature, the uh, ideal nature analog to digital conversion ADC that can be happened, and that is possible by using certain modulation techniques. Those are known as baseband modulation. But there have another modulation technique which is known as pass band modulation or band pass modulation. Before that, I want to show you this particular basic model of wireless digital communication link. Last day I told you, first information source information that may be passed to the source encoder, then it may be passed to the encryptor because we need more security. After that, channel encoder, it is something related to compression, and it is something related to some bits addition. Then all those things must be passed through certain modulator, and before that we need to think about this modulator. What is this? This is something related to our pass band modulator. Okay, so pass band modulated output that may be converted in terms of RF conversion. RF up conversion means the signal is transmitted through the antenna, transmitting antenna. After that transmitting antenna, when the signal is transmitted, that signal may be passed through the channel. And channel means it is the media, wireless media or wired media, anything is possible. But what we need right now, the wireless communication is the most important thing, where the links that is not connected, and because of that the networking policy is something modified, and it is possible to connect anywhere through our air media. And it is something maybe associated with more important thing related to digital communication technique. And then this wireless channel, through the wireless channel, the information may be propagated uh, from the RF upconverted transmitting signal transmitter. The transmitted signal may be passed through the channel, and when the signal may be captured by the receiver, and that is obviously receiving antenna, and that is commonly known as RF down conversion. After that, that signal may be demodulated first. Now obviously before that you may ask me that signal may be amplified, because after certain propagation the signal strength or signal amplitude or signal power that may be affected, and some attenuation may be takes place. So when the signal may be propagated, after that first we need to uh, modify in terms of its boost up through the enhancement. I'm talking about the enhancement in terms of power or amplitude that may be boosted up, which is possible using RF amplifier. So what I need amplifier. And when the signal is amplified, then first of all, that signal first demodulated via some demodulator. Okay, these are the pass band demodulator. Then the process is something just opposite. So one by one, the information is passed to the source encoder, then encryptor, then channel encoder, then next to the modulator, then RF up conversion, then wireless channel, then RF down conversion, then demodulator, then next to the channel decoder to decode the information. After that, decryptor, because when the signal is encrypted for better security purpose, now we need to decrypt it. Now, after that, that signal is passed to the source decoder, and after that source decoder, that signal may be received to this information sink. And this is the procedure, and this is the basic model of wireless digital communication system. And these are the various links. Okay, so after that, I'm talking about digital modulation. What kind of modulation? Already I told you, pass band or band pass modulation. There are three attributes for any signal that can be defined through the three attributes. One is amplitude, next is phase, and another one is frequency. When I'm talking about the digital modulation process, corresponds to the switching or keying the amplitude or frequency or the phase of the carrier wave according to the incoming message signal. But what kind of message it is? It is obviously digital form. It is not analog form. When the message in terms of analog form, then that modulation is known as analog modulation. But this message is now in form of digital nature. So uh, after that, when I'm talking about digital modulation techniques, first shift keying technique, one term is important, keying. What is keying? Keying means switching. Switching, the most important parameter that is important for this switching purpose, that is amplitude, when it is known as amplitude shift keying. Next to that, your phase shift keying. When phase that is switched, okay, phase means 0 to 180 degree, or it may be switched to 0 to 45 degree, then 45 to 135, 135 to 225, another few stages there. There may be other modulation technique also related to phase shift keying, whatever it is. But next to that, frequency shift keying, when the frequency is most important, because some frequency that may be used either low frequency or high frequency, and that frequency may be used for switching purpose, then it is known as frequency shift keying. And digital modulation, when the baseband data I'm considering in form of either unipolar signal or polar signal. You may ask me, what is unipolar signal? Unipolar signal means there have some bits 1010 pattern. When I want to write 1 means it is the corresponding voltage level is plus 5 volt level, and 0 corresponding voltage level is 0 volt, then only one direction, 0 to positive direction. There are no more negative side. That means unit directionalities. So that's why it is unipolar signal. It is unipolar signal. On the other hand, if I consider 0 volt means minus 5 volt and 1 means plus 5 volt, that means there have two polarities. One is for plus 5, another for minus 5. Both directions are there. So when both polarities may exist, then that is known as the polar signal. Polar signal. There may be another another signal that is known as bipolar. What is bipolar? You may ask me, what is bipolar? Bipolar means actually when one is defined by plus 5 volt. 0 is defined by 0 volt. But next one, when it will come, then that time, if previous one is defined by plus 5 volt, then next one should be defined by minus 5 volt. That means 0 is always 0, but alternate one will be defined by plus 5 volt and then minus 5 volt, then plus 5 volt and minus 5 volt. If 0 is there, binary 0 is there, that is always defined by 0 voltage. But first one, if odd one is plus 5 volt, then even one should be minus 5 volt. Then again next odd one should be plus 5 volt. That means alternate change should be there. That's why this kind of line coding, these are known as line coding, unipolar line coding, polar line coding, bipolar line coding. Okay, so this third one, bipolar, there are two polarities, but 0 is always 0. But based on the one, even or odd, we are getting plus 5 volt and minus 5 volt. So bipolar nature that may be found only due to switching of different ones, even and odd. Based on that, we can say alternate switching may be found. Alternate switching may be found due to one, even one and odd one. That's why it is known as alternate mark, M-A-R-K, mark inversion. Alternate mark inversion. There are three line coding techniques. One is your most common thing, that is known as your unipolar line coding. Next to that, polar line coding. Unipolar means 0 is always 0 volt. Polar means 0 is minus 5 volt. And in case of bipolar line coding, 0 is always 0 volt, but alternate one that will produce either plus 5 volt or minus 5 volt. Even one, if it is plus 5 volt, then odd one should be minus 5 volt. If odd one is plus 5 volt, then even one should be minus 5 volt. Alternate mark inversion, inverting plus 5 to minus 5. This inversion can be happened due to this bipolar line coding. So based on that, we can use different line coding technique for our baseband data. If our information is 1, 1, 0, 0, 1, 1, 0, 0, 1, and I'm taking the unipolar line coding, and I'm taking unipolar line coding for some modulation technique which is known as amplitude shift keying. For amplitude shift keying, we will use the unipolar line coding. You must remember, for amplitude shift keying, we want to use unipolar line coding. Why? I will tell you later. Because of that certain mathematical reason, I will define it. But before that, I want to tell you, there have one most important thing, that is baseband signal, which should be the unipolar line coding. And in case of your phase shift keying, the baseband line coding, baseband signal that may be found in terms of line coded nature, that should be polar form. That should be in polar form. So first of all, when I want to define the amplitude shift keying, I'm considering it is unipolar line coding. So when it is 1, 0, 0, 1, it means 1 means plus 5 volt, 0 means 0 volt. Again 0 means there have 2-bit duration. There have one particular point is there in between this particular duration. If I can consider, it is twice t. If it is t only, if the time duration for this pulse is t, then I can say the time duration for this pulse is twice t. That means there have two pulses and both of the pulses signify 0 and again 0. So what I can write? 1, 0, 0, then single duration, that is positive duration, I can write 1. So 1, 0, 0, 1. If 1 is defined by plus 5 volt, 0 is defined by 0 volt, then I can say plus 5 volt, then 0 volt, again 0 volt, then plus 5 volt. This is the baseband signal in form of unipolar line coding technique. Next to that, when I want to use ASK modulated signal, what we will get? We will get for 1, when it is 1, the pulse it is present, that means plus 5 volt is there, and that time some carrier signal is propagated. That carrier signal is present because some plus 5 volt is multiplied by certain carrier signal, existing carrier signal. But when the 0 bit is there, 0 bit means the corresponding voltage level is also 0, that means ground potential. That ground potential, when it is multiplied by carrier signal, we will get the output exactly 0 volt. So when it is 0, we are getting 0 output. Same thing for another bit duration. When it is 0, we are getting same 0 output. That means here it is on, now it is off, again it is off. But when again it is 1, that means it is on, and that time plus 5 volt is multiplied by carrier signal, we are getting the on situation. So what we can say? On, off, off, on. That means it is on, off keying. This is known as on, off switching or on, off keying. Okay, so this is the alternate name of ASK, OOK, OOK or ASK. ASK means amplitude shift keying, or sometimes it is also known as on off keying or on off switching. Now next to that, when I'm talking about phase shift keying, then we need to think about these bits 1001 that should be defined by polar line coding technique. And that time 0 is defined by minus 5 volt. Instead of 0 volt, now it should be defined by minus 5 volt. And 1 should be defined by plus 5 volt. Now, when I'm talking about BPSK, B for binary phase shift keying, because there have only two different phases, okay. One is defined by 0° phase, 0° phase and 0° phase shift, and another one is a 180° phase shift over the original carrier signal, when 0° phase shift, that means original carrier and the output carrier, they are same. But when 180° phase shift over the original carrier, that means we are getting just the inverted nature of the original one, and that's why we are getting two different form. That's why it is binary phase shift keying. There are two different phases, so binary phase shift keying. So based on that, when it is 1, I'm getting this is plus 5 volt, and this is associated with this system. But when this 1 to 0 switching is happened, then something is inverted. Directly, this switching may be found over here. There have one inversion. It is not directly started from this position, just 180° phase shift between this transit points. This is the end point of this pulse duration, and this is the starting point of this pulse duration, and we are getting just 180 degree phase shift over there. But when it is again 0 to 0 switching, then it is continued. No more phase shift over there. But when it is 0 to 1 switching, then again we are getting 180 degree phase shift in between these two transit point. So this is known as binary phase shift keying modulated signal. Okay, on the other hand, when I'm talking about BFSK modulated signal, there have only two different phases, frequencies. One frequency is defined for 1, another frequency is defined for 0. So when I'm getting negative pulse due to 0, that time that is defined by low frequency. That means the time period is higher. On the other hand, when it is 1, that means the positive pulse is there. That time we are getting the frequency is higher. So when it is 1, we are getting high frequency. When it is 0, we are getting low frequency. We are getting low frequency. In case of our laboratory, you may obtain just opposite thing. That is just a different issue. This one, when it is 1, you may obtain a low frequency. For 0, you may obtain high frequency. Just that is based on the device only, nothing but the issue related to some common mathematical technique. That is absolutely based on the frequency switching. Low to high frequency switching or high to low frequency switching, anything may be happened. Okay, but frequency should be different. Frequency should be different. If 1 is defined by low frequency, then 0 is defined by the high frequency. If 1 is defined by the high frequency, then 0 should be defined by the low frequency. No more other concepts behind this. So after that, now I want to show you the different mathematics behind this. So when I want to write those mathematical concepts, so I want to share the window. First, I want to write some mathematical form. That's why I want to show you basic mathematical form of ASK. If it is ASK, for 1, how to define it? For 1, when it is 1, the signal that is defined by AC cosine omega CT. That means our carrier signal is transmitted. When it is 0, when the binary input that may be found as 0, so if based on the unipolar line coding technique, 0 volt is multiplied with our original carrier. So we are getting what? We are getting 0 volt at the output. So what I need, this is different issue. First, I need this situation. That's why we are using unipolar line coding. Actually, I need on for 1. For 1, I need on, and for 0, I need off situation. If I want to define this thing, how to do that? If I want to do this, it is possible only when I can define it by using unipolar line coding. Otherwise, it's not possible using polar line coding. That's why I want to code this signal by using unipolar line coding. Clear? So you must remember, this is not our issue. Our main issue, what I need for ASK, or in case of ASK, the mathematical expression, that is modulated signal expression, that is defined for 1, it is on. For 0, it should be off. if I need it, then how to define this baseband signal 10 by using unipolar line coding. On the other hand, what about BPSK? In case of BPSK, we need to think about something different. When it is 1, it should be defined by AC cosine 2 pi fct or AC cosine omega ct. And that time I can say omega ct, that is added with 0 degree phase shift. So that means it is absolutely same with the original carrier. On the other hand, what about 0 for BPSK? For 0, it should be AC cosine omega ct, because I need two different phases. How to define all those phases? If there have two combinations, if there have two combination 1 and 0, how to define it? You have total phase 2 pi. After that the signal is then again come to the same point 0. Okay, so if it is 2 pi and there have two combination, so how much phase shift over there? Maximum pi, maximum 180 degree phase shift over there. So that's why if it is 0 degree, next to that, when it is 0, how much maximum phase shift I need? I need plus 180 degree. So I need to add the phase, that is pi phase shift. So there have two phases. One is 0 degree, another one is 180 degree. Instead of BPSK, if you think about more phase shifts, like if I need four phase shifts, and based on that, there have another modulation technique that is known as your QPSK. QPSK. And for four phase shift keying, that is known as QPSK, there are four different phases. Why four different phases? Because four, that is as that may be defined by four different combination. How to define it? By the binary bits. That may be defined by 00, 01 and 1011. So there have four different combination based on the 2 bits. Okay, based on the 2 bits, we are getting four different phases. And how to define it? By using maximum, you have 2 pi is the phase angle. So there should be maximum pi by 2 phase shift with the original signal and corresponding signals. So if I can, I want to start with the corresponding signal AC cosine omega ct, AC cosine omega ct with the original phase shift. If I am considering pi by 4, if I am considering pi by 4, next phase, the next phase should be pi by 4 plus pi by 2. That means it is 3 pi by 4. Next phase should be just 5 pi by 4, because 3 pi by 4 to addition of another pi by 2. So I can write 5 pi by 4. Next phase, that should be 5 pi by 4 plus another pi by 2. So what I can write? I can write 7 pi by 4. So I am getting four different phases. One is pi by 4. Next to that, your 3 pi by 4. Next to that, your 5 pi by 4. Next to that, your 7 pi by 4. How to generalize them? By using one common mathematics. We know that in any odd terms, there have only odd terms, 1, 3, 5, 7. How to write odd terms? That may be defined by 2k plus 1 into pi by 4. You may say that I can write 2k minus 1 2k minus 1 into pi by 4 also. Yes, you are right, but when k is 0, that should be started from minus pi by 4. But I want to start k equal to 0, and that should be started from pi by 4. That is possible only when I can write 2k plus 1, not 2k minus 1. That's why it is 2k plus 1 pi by 4, that is the initial phase and corresponding phases. Okay, so this is about QPSK. There are other phase shift keying techniques also, MRE phase shift keying, DPSK, differential phase shift keyings, etc., etc. But I will tell you later. Today I am discussing about only BPSK. There are MRE PSK, DPSK, etc. And there are other modulation techniques also related to phase shift keying. But next to that, after that BPSK, I want to tell you another modulation technique that is known as BFSK, binary phase shift keying. In case of binary phase shift keying, I told you for one that is defined by high frequency or low frequency, whatever it is, but I want to write that is defined by cosine omega 1 t. That means one frequency that is defined by omega 1. Here the frequencies are absolutely same, omega c, omega c, omega c. Only the amplitudes are different. In case of BPSK, phases are different, but in case of binary frequency shift keying, frequencies are different. So what about zero? When I'm talking about zero, I'm getting just another important frequency, that is cosine, AC cosine omega 2t. So what happened? I'm getting two different frequencies, omega 1 and omega 2. So I mean, it may be possible either omega 1 more greater than omega 2, or according to your device you can say omega 1 more less than omega 2, whatever it is. So we are getting three fundamental passband modulation techniques, BASK, binary amplitude shift keying. Then next to that BPSK, and in case of BPSK we are getting what? We are getting some inversion. How to do that? By using only polar line coding, because there have the amplitude that is absolutely same AC, but what I need inversion. That is possible only when I can use polar line coding. Same thing, what about our BFSK? Amplitude is always same, but based on the 1 to 0 switching, it may sense that some positive to negative triggered may be happened, and it should be for high frequency to low frequency switching may be found at the output. So that's why I'm getting this output like high frequency and low frequency for BFSK by using another polar line coding technique. Now question, today I want to show you only the modulator block related to amplitude shift keying. In case of amplitude shift keying, what about the modulator block? If I want to show you the amplitude modulator block, then you will get something like one modulator which have this kind of output. I want to show you. This is the output. This is known as on-off signaling. I told you. This is the bit duration, TB, and at that duration 0 is off and 1 means on, and for 1 duration the carrier is present, for 0 duration carrier is absent, and at that time the signal is defined by this way. S1t is the modulated signal. For 1 it is root 2 EB by TB cosine 2 pi FCT. For 0, it is S2T is equal to 0. You may ask me, sir, why root 2 EB by TB? Instead of AC, why should I write the root 2 EB by TB? That I want to show you. Now, just think about your AC. AC is the amplitude. How to define your power? Power may be defined by AC square by 2. It is the power, the root means square power. Okay, that is carrier power. If I want to multiply it by TB, then I'm getting the energy. So it is our EB. You must remember energy is the fundamental thing, and we need to define this is for most important thing about digital modulation technique, because ultimately we need to draw one energy versus phase energy versus phase uh, diagram, and that is most important. I will show you later, but first of all, I want to compute what about AC in terms of EB. If I want to compute AC, then I can write AC squared is equal to 2EB, 2EB by TB. If it is true, then I'm getting AC is equal to root 2 EB by TB, root 2 EB by TB. This is the fundamental expression about our amplitude in terms of energy. So this is the reason when I'm getting root 2 EB by TB, that is the reason behind this. Next to that, uh, how to compute the energy per bit. For 1, energy is present. For 0, nothing is present. So what I can write 0. Then for 2-bit duration, I can write overall value is defined by computation of mean value of 2, mean value total time duration based on the 2 bits. I can write 2 bits E for first bit for 1 and 0, that means for 0 bit. So if I can add them and divided by the 2 bits, then I'm getting overall bit energy. So E is equal to twice EB, that is average energy per bit. Now this is everything about the amplitude shifting, and when I'm talking about the another important issue related to our uh, method, I want to show you, that is the technique. I want to tell you about the modulator, how to draw the modulator. First of all, what I need the unipolar line coded signal. I need unipolar line coded signal. Unipolar input, unipolar input, line coding signal as the binary input. And what I need one system that is mostly known as product modulator. Why product modulator? Because the input signal is directly multiplied with our carrier signal. Then I'm getting, when it is positive, then I'm getting original carrier. When it is 0, I'm getting just 0 is multiplied by my original carrier, and that is simply output as 0. So when it is product modulator, then only it is possible. So it is product modulator. And next to that, I need to apply one carrier signal, and that is locally generated carrier, locally generated high frequency carrier from the certain local oscillator, certain local oscillator. I can write local oscillator. And after this product modulator, the signal may be passed through certain band pass filter, and I'm getting my output as ASK signal. This is the basic block diagram of our ASK modulated signal. Instead of unipolar, if I can just suppress this uni term, I'm getting only polar line coded signal. Okay, now when polar is line coded signal is applied to the product modulator, and AC cosine omega ct signal is applied to the product modulator, and that can be passed through the BPF, then I'm getting, instead of ASK, I'm getting PSK. I'm getting PSK. So these are the most important block diagram about ASK PSK. If you have any query, any question, please join at the necessary meeting code immediately. Okay, thank you. Please join there.